right, it is Friday afternoon, and we're going to sit around and do a little math physics. Exhilarating, so much fun. All right, so now, all right, that's not B. All right. I rearranged everything here for a second, and then mixed up. Okay. Calculate the electric field from a distribution of charge. We have to add up the fields from an infinite number of charges. Okay. So, in other words, let's just say that we're talking about a line of charge. Okay. So if I had something like this, okay, I have to add up all the electric fields due to each one of those little charges. Okay. Now, the assumptions that we make here, okay, is that each one of those charges is infinitely small, and that there are an infinite number of them, okay? Such that when we multiply the infinitely small by the infinite number, we wind up with a very specific charge that will be on here. So we get charge Q. Actually, we're going to use lowercase q for this. Now, here's the thing. Okay, this is a bit simplification. We know that this charge is discrete. Each one of those charges is discretely small. That each charge has 1.6 times 10 to the negative 19th coulombs on it. We know that they have a definite size. That if you're talking about the size of the atom, it's well, the nucleus of an atom. If you're talking about protons, you're talking about 10 to the minus 14th or 15th. The electron we actually assume to be infinitely small, to be a point charge. There is some attempts to actually measure the size of an electron, but it's not going very well. It's because it is so very small. But these really small simplifications usually work really well. Okay, everything that we do, okay, we have to make some simplifications, and these simplifications work really well. But the fact that we have these charges being quantized, okay, the fact that the size is quantized, it was those kinds of assumptions that when we broke with those assumptions that it was infinitely small particles. Once we broke with that, okay, that's what got us to quantum theory. Okay, we were able to basically, essentially, the origins of quantum theory started with somebody saying, well, instead of doing an integration like what we're going to do, let's just assume that we make the additions of extremely small little results. Okay, everything is added up just a little tiny bit at a time, and this is what was in what was called black body radiation. And when he did that, for some reason, it was a curiosity more than anything. He got the curve that he was looking for instead of a curve that everybody else had gotten by using integration. By breaking it down, by breaking with the assumption that this is breaking with the assumption that this is a continuous line of charge at a very, very small scale, he was able to essentially solve a problem that was in that physics was having at the time. It was really considered the last problem that physics had to solve, and then everything was going to be done. Then when he solved it the way that he did it, physics was completely unsolved. It was completely different from there on out. So anyway, all right, let's go on from there. All right, we're going to look at the electric field from a very small scale. Okay, so if I have a little tiny point charge, okay, little tiny, I'm going to call this instead of Q, I'm going to call it a dQ. Okay, the little tiny electric field from that little tiny charge is going to equal 1 over 4 pi epsilon naught dQ over r squared. We're going to say that we're at some point P here. That's a distance r away. So now that little tiny charge here creates an electric field at this point. Okay? We now know the direction. Okay, the electric field is going to point out in that direction. We're not so much concerned with that right now. But let's just say that I start putting out a whole bunch of these little positive charges. In fact, I'll just make little positives. Okay? We want to figure out what the electric field is from that distribution. Okay? Now, here's the thing. When we start adding them all up, okay, we're going to use calculus because we're going to assume that it's a continuous distribution. Here's the thing, though. We don't like to integrate. Okay? For those of you in Calc 2, we like to integrate over distances. For those of you in Calc 1 or FunCalc, we like to integrate over distances. We don't like to integrate over charges. It doesn't really make a whole lot of sense. Okay? So what we're going to do is, instead of calling this dq, okay, we have something that we're going to call lambda. We're going to come up with these what are called charge densities. Lambda, sigma, and rho. This is going to be the linear charge density. This is the area charge density. And this will be the volume charge density. We usually think of density always being mass divided by volume, but it doesn't have to be. Anything can be a density, okay? So if I look at linear charge density, what do you think a linear charge density would be? What, in English, go ahead and answer.
Until they pack the charges.
Okay, so if mass density is mass per unit volume, if you're talking about linear mass density, it would be mass per unit length. So what do you think linear charge density is going to be?
Q per unit work.
Okay. It's going to be the charge per unit length. Okay. So now, lambda, and again, lambda actually could be for mass density. It could be for the electric field density. Usually talking about volumes or areas there, but lambda represents a linear density. Okay. Most of the time, when you're talking about chemistry, you're talking about mass density. But physics, we get a little bit more creative when we talk about lots of different types of densities. Okay? Lambda is equal to, for what we're going to talk about, linear charge density, lambda will equal the charge per unit length. So if I have an object here of length L, okay, and charge Q, let me just put this, let's make it a positive charge here. Okay? This will have length L, and we'll have a charge Q1. Okay. Q, therefore, is equal to
Steve, Alan, can you stop by the main office,
the
please?
density
Alan, to the main office.
times L. Now we can do what's called implicit differentiation. Okay, did you guys do that? Okay. We can say that this is dq lambda dl. Because we assume that the charge density is going to be constant over the length. It doesn't have to be, but it makes things a lot easier if it is. When it's not, then you've got a more complicated problem to deal with. So now, I'm going to substitute this dq right here. I'm going to substitute that in right there. So my differential electric field will equal 1 over 4 pi epsilon naught lambda dl over r squared. Let's make sense of what this is up here. Let's say I'm looking for the electric field at that point right there. let's say that the charge is equal to, what do I have over here? 5 microcoulombs. This is point P. I'm going to say that the length here is 0.1 meters. And I'm going to say that this is 0.05 meters. Okay, between point P and our bar. So now, in doing this, okay, lambda is going to be the charge per unit length. It's going to be Q over L. Okay. I'm going to have over the DL here, my R, okay, for this problem, think about what R would equal in this case. R will equal 0.05 right here, plus, let me come up with it there. Okay, it's usually the other way around. I'm going to say we're going to integrate like this. Just say that we're right here, to that point. So 0.05 plus L. So that distance that you're away from here, okay, is going to be that 0.05 plus L. Now I can't, you say, well, why don't I just figure out what it is here? Well, if I'm right here, then, you know, you're right on top of it, your electric field gets, does some weird things near the edge, okay? You can actually see what happens when you plug in 0 instead of 0.05 meters, okay? Now, I want you guys to try that up for homework. Now you might say, well, right now I can't solve that problem at all. Well, let's take a look at some other problems and see what you can do. That's a challenge problem to you guys right now. Okay. So let's take a look at a ring of charge. Okay, we're going to look. This is a little bit harder. This one's a little bit more advanced than the one that I'm going to do next. Okay, but if we think of it as on a line, we can solve this kind of problem, but it's a little bit more complex than what I'm about to do. And I want you guys having some practice at doing at least one of these. You guys can do this, especially if you're in BC, if you're in AB at this point, okay? Set it up. Try setting it up, and you're going to use what's called, you're going to plug it into Wolfram Alpha, or you just go to the Wolfram integrator site, and you can do it from there. But you guys can set it up. So now let's take a look at this. Let's just say that I have a ring of charge. Okay, this is a ring, it's not a disk. Ring, not a disk. Okay, this has a radius r. I want the electric field, the height z along the central axis. Let's center that a little bit better. Okay, so this central axis is not a real thing, but I want, I'll call this point P right here. Okay, this is along the central axis. It's a height z above it. So I'll write this off to the side. Yeah, the height there is z. Now, a couple things about this. I'll write this over here. That's z. Okay. This right here, the distance to, whenever I'm talking about this kind of r here, okay, from this little spot right here, this is going to be this ds. This little part right here. Okay. This is a distance we're going to call little r. This length is r, this is z, this is theta. We'll call that angle theta. Now we want the electric field from this little part right here. Okay. Does that make sense? This little part right there. So now, I set it up a little bit first. Okay. We're going to say that dq is equal to lambda ds. Now, you say, well, why are we using ds this time instead of dl? Okay, arc length is usually talked about in terms of s, so there's no special reason, just what it is. Now, here's the thing. If you look at this, the electric field that's created at this point. Due to this point right here, the electric field is going to point out like this. I'll call this dE1. I'll say that this is ds. Does that make sense? From over here, the electric field is going to point out and away from you. Okay. If I had a charge right here, with a positive charge right here, the electric field at this location would go out like that. Make sense? Okay. Just say I have ds2 over here. Okay, another little part. What way would the electric field point from that? It would go up like this. Okay? dE2. This is angle theta. This is angle theta. Everybody okay with that? Okay. That these angles would have to equal this angle here. All right. What happens to the side-to-sides? Okay, the side-to-sides are going to cancel out. All we care. So what direction is the electric field going to be at this point due to this ring of charge? Straight up. Okay. More than anything else, that's something that I want you to get out of this. Okay. The math is going to get dense. Okay. We have to do all sorts of integrals. Crazy. It's ridiculous. But understand what direction the electric field is going to go. The electric field is going to point up. Okay. So now, what we're going to look at here, instead of looking at the whole thing, we're going to look at, okay, instead of looking at this whole thing, we're only going to look at this part of it. Well, if this is dE, and this is angle theta, what part is this going to be right here? You can pause it if you have to. Think about that. This is dE, this is angle theta. What's the up part of it going to be? Okay, so what we're going to look at here, we're looking at dE cosine of theta. Okay, that's really what we want. We want dE cosine theta. Now, let's think about what's constant here. The r is actually going to be constant. Little r is constant. Z is a constant. Big R is a constant. Theta is a constant. Now we want all these constants because it actually makes the integration a lot easier if I can pull all the constants out. Remember, in integration, okay, you can pull all the constants out that you want to. And see how that works out. And if that works out better for you. Okay? So now, I set this up. dE will equal, I'm going to change back to blue. dE is equal to 1 over 4 pi epsilon naught dQ over r squared. Okay, just as we had before. Okay. We know that dQ equal lambda ds. Okay, there. Now, here's the thing. This length r. Okay. Most of the time we're not given this. Okay, we're given the height above the ring, and we're given the radius of the ring. So instead of calling it in terms of little r, we're going to put it in terms of big R and z.
Simone, please come to the main office.
So now that r is going to equal the square root of big R squared plus z squared. Okay? Big R is the radius of the ring. Little r is the distance from the ring to the point. Okay? Now, we want to do this. Okay, we want to put in cosine theta as well. Okay? Cosine theta will equal, okay, here's theta. Cosine is equal to adjacent over hypotenuse. So what's that equal in this case?
0.
Z over R. Now, here's where it becomes a little annoying. Well, a little more annoying. We don't want little r. So instead of z over little r, we say z over square root r squared plus z squared. So let's put this all together.
Isn't that squared though?
What's that?
Over R squared. No?
What's that? I'm sorry.
Well, no, if it's,
Oh, okay, yeah. We'll get there. I'm just saying r is this.
Alright.
We're going to use r squared.
Alright.
So now, we have, again, we don't want dE, we want dE cosine theta. dE was 1 over 4 pi epsilon naught. dQ, which we said was lambda ds. Okay, we're just doing a whole bunch of substitutions now. Over r squared is going to equal big R squared plus z squared times cosine theta. Cosine theta is going to equal z over square root of r squared plus z squared. Okay. So now my electric field will equal the integral of dE cosine theta, not worrying about limits of integration at this point. Because we've got to see what we're integrating first. Which is equal to the integral of 1 over 4 pi epsilon naught. Combine this, lambda z ds over r squared plus z squared to the 3/2 power. Now, here's where a little beauty comes in. Okay, like I said, we only want to integrate, we want to pull all constants out for the most part. Maybe it's useful for in integrating, but for the most part, we want to pull all the constants out. 1 obviously is just a number, 4 is a number, pi is a number, it's a constant. Epsilon naught is a constant. Lambda, constant. Z, constant. ds, that's what we're integrating over. R is constant, z is constant. Everything in this integral is constant. So my electric field is equal to 1 over 4 pi epsilon naught lambda z over r squared plus z squared to the 3/2 power integral of ds. Now, this is the integral of an arc length. We're going to integrate as we go around the circle. So if I start off here at this, I call this 0. Okay, if I call this point 0, and I integrate all the way around, how far around is that?
360 degrees.
Okay, what would be the distance over which I'd be integrating?
Oh, 2 pi r. No,
2 pi r. Okay, so I'm going to integrate from 0 to 2 pi r, big R. Okay, Kevin, you're not in BC Cal. What's the integral of ds?
For,
Anything?
pi r?
Okay, well, you actually took the definite integral of it, yeah, okay. The integral of ds itself is going to be s, and then
Oh,
when you
okay.
plug in the limits, yes, it'll be 2 pi r.
Okay.
So I wind up here with 1 over 4 pi epsilon naught lambda z, as you pointed out, over r squared plus z squared to the 3 halves. This whole thing, okay, is s. It goes from 0 to 2 pi r. Okay, so now we wind up with 1 over 4 pi epsilon naught. Lambda, well, I can put lambda back, I can substitute back in for lambda. Okay, lambda was the charge per unit length. So lambda is equal to charge over 2 pi r. So this is q over 2 pi r
Times 2 pi.
times z all over r squared plus z squared to the 3 halves times 2 pi r, plugging in for yes there. 2 pi r's go away. Okay, I'm left with an electric field of 1 over 4 pi epsilon naught. Gotta hope this works out right. QZ, I haven't looked at my notes in a while. R squared plus Z squared with 3 halves power. Whew. Got it right. Okay. So this is the electric field. At a point above the central axis of a charged ring. Okay. Now, it's a lot of math. It actually simplifies out a lot, though, too.
Can I just use K instead of 1 over 4 for like just to clean it up and put it back in the end?
In this case, it works out okay. In other cases, it starts not working out.
'Cause
When
you're
we get to
dividing
Gauss's, really when we get to Gauss's law, that's where I'm going to be a little bit more of a stickler for 1 over 4 pi epsilon naught.
Does
as
pi
opposed to-
cancel out or something? And then you're
Yeah.
Okay.
You wind up with, I mean, we look at some simple cases and some where it's still 1 over 4 pi epsilon naught, and then some other cases where it goes away.
Okay.
Now, all right, good. Hit pause.
Just hit record again. Where is it? Hit record
Same
again.
button, yeah.
5